Hello, everybody. Welcome to the, I believe, 12th week of CAT2. Today's topic is going to be modal analysis with ANSYS. One of the luxuries of being a lecturer is that you can become more and more lazy. And I've been extremely lazy to use FEM software myself for quite some years now, I have to admit. And it's pretty easy to be lazy at MESD too, because I'm surrounded by young people who are eager, skillful, highly qualified when it comes to the use of simulation software, obviously. So this is why during today's demonstration, I will hand it over to Mr. Chinnawit, who is a research assistant at MESD. And he will demonstrate to you how to use the ANSYS software to do a modal analysis. But before we'll start with that bit, I took the liberty of doing this little introduction to the topic of modal analysis first, right? And as you know, as you might already know me, I always try to make a connection to music and musical instruments whenever I have a chance. Let me mute that thing first. And of course, in the topic of modal analysis, this is obviously a very great chance to introduce music and musical instruments because we're talking about vibrations. Modal analysis is something you don't always have to do on a computer or with simulation software. And the few students of you who chose the special topic in vibration and acoustics know already that basically modal analysis is an activity to find out what modes a vibrating system has. And you could do that in an experimental way. And today we'll be doing it by means of simulation. And I guess nowadays, but you would have to ask Ajahn Kemapat, who's joining today too. Nowadays, anyone would do both at the same time, running an experimental analysis and running a simulation of the same thing, just to make sure that the results of both don't contradict each other. Anyhow, so introduction first. Vibration and acoustics are connected, of course. If something vibrates and it moves air, then you can hear it. So this is why we'll, as an example, we'll use something you can hear, which is a guitar. And I'll first demonstrate it on an actual instrument, and then I will show you the same thing on a slide, just to make sure that everybody understands what I'm talking about. Now, I guess you can guess very well that the things that are vibrating on a guitar are the strings. The rest of this beautiful instrument is just designed to amplify that sound and, of course, to play it. So here we have the fretboard. We have 6 strings on this guy, although I just need one to demonstrate what I'm talking about. And then you have these little metal bars here, and they're called frets. And their purpose is you can shorten the length of the string to create different frequencies, of course. So I think I'll be using just that low string. Just if you're interested, that would be an E, right? And if I want to play, let's say, a scale on that, I could just finger the frets, which you can't see now, shortening the length of the string to create different frequencies. But that is not what we're talking about today. We're just talking about the different frequencies that can be produced with only one string without shortening it. And so as you hear already, if I just pluck the string, you get a pretty low note, right, that has a specific frequency. What you can actually hear is a lot of different frequencies at the same time. But the way we hear and what the brain makes of the information that our ears as sensors get from the vibrating air, we hear a so-called pitch, and that would be the lowest frequency that we can hear. So in this mix of frequencies that the string is producing, we perceive the lowest frequency as the pitch of the musical note. Okay. Now, why am I claiming that it is many frequencies that we're hearing? Well, because I know if it would just be one frequency, the sound would be different. It wouldn't sound like a guitar. It would just sound like a computer-generated sine wave with only one frequency. Okay, so again, I'm plugging the whole string, pretty low note, and as you'll see in the presentation later on, that note comes with a specific shape of the vibrating string. Now, what I'll do is I'll hold my finger touching the string exactly in the middle, and by some neat coincidence, no, it's not really a coincidence, it's designed that way. That position would be the so-called 12th fret. Okay, on a guitar you can tell 12th fret, usually it's marked by 2 dots or a different kind of marking on the fretboard. So I'll touch it here and pluck the string, and I hope you can still hear that, but I have the microphone very close to it. It is it's a musical note 1 octave over the original tone, so it's also called an E, and the actual frequency is double the frequency, right? So notice I'm not pushing the string down onto the fret or the fretboard. I just kind of dampen the string right in its middle at the 12th fret and pluck it again. Okay, so maybe you can already imagine that the original shape, the first mode of the vibrating string, was basically like half of a sine wave, right? So with its maximum excitation while it's vibrating in the middle. Now, when I put my finger there, it cannot vibrate in the same shape, in the same mode. So what the string is now doing, it's basically separating itself. So maybe you can already imagine that the form or the shape of that vibration is now a full sine wave with what we call a node in the middle. So basically, I created a node in the middle of the whole string by putting my finger there. So the resulting shape, that would be the second mode of that string, has a node at that position, and the word node means there is no excitation of the moving body at this point. Okay, so musically it's an octave, it's twice the frequency, and when we're talking about modal analysis, that will be the second mode. Now I can do that at other positions too. So let's say I've halved the length of the vibrating string. Now, although the whole length is actually vibrating, but I put a node in the middle, I can do the same thing by cutting it into thirds. Now, I could just measure the length of the string and then divide that length by 3 and then find that position. But actually, I know it already. That position would relate to the 7th fret. So here's the 7th fret. Let me just hang to see what this chat message is saying. Oh, Siphon kicked herself out. Okay, so 7th fret would be a third of the length. So first the original frequency again, then this would be the second mode, and now I'll put my finger on the 7th fret. That is also a musical note. That would be the 5th of the octave of the original note, and that relates to half of 3 times the original frequency. So the original note for those musicians among you, original note being an E, the 5th would be a B, a natural B, but 1 octave higher. Okay, so that is what I get when I cut the whole length into 3 parts. I can cut it into 4 parts. That would relate to the 5th string. Also, there's one more position, but it's somewhere on the right side. So it's the 5th. Hope you can hear that. So original, that is the 1st mode, 2nd mode, 3rd mode, 4th mode. And it goes on and on. I can cut it into 5, 6, 7 pieces, but they're kind of hard to find now. I think that will be 5. I found it. Oh, 6. I found it too. And so on, right? So people actually turn that into music. You can make use of that musically. But enough of music for now. Now we'll go into science. And let me just quickly find my presentation. So I hope, but I assume from my recent experience, you should be able to see me now. So then here's my title slide. And of course, I have to show you another guitar. This is an electric guitar, but vibration-wise, we have the same things happening here. So as you probably can tell from the image, we have quite a lot of string there, but the actual vibrating bit is only from the so-called nut on the right side to the bridge on the left side. So I put in those two gray lines and the red line to show where the actual vibrating part of the string is, the musical part. And now let's see what happens if I pluck it without any finger on it. So you have the whole length of the string vibrating in the first mode. You see it now. So you see that it's obviously symmetrical, typical sine wave, and right in the middle, this is where you have the maximum excitation. And you would call that, by the way, the anti-node. I've already said what the node is. You could claim you have nodes at the two ends, but I'm not even sure, I'm not the vibration expert, if that's really called nodes, because that's just the end of the string where it's constrained, so to speak. So now let's look for the middle of that, simulating what I've just done with a real guitar. And you can see on the image of the guitar, that will be the 12th string. So that's right here. You see the gray line in the middle. It extends from the 12th string, and it meets the red line right in the middle. And the shape of that vibration, which we just heard, looks like that. So now it basically looks like a full sine wave. So the wavelength would be double the wavelength, so to speak. Half the wavelength, very sorry about that. And frequency, the resulting frequency would be twice the frequency. Now we're looking for the 7th fret, which is right here. You can already guess that relates to a third of the original string length. So I could actually dampen it on a different position too, on the left. Let's see if you can see my mouse. But there's no fret here. That would be somewhere where this weird piece of technology is. That's called a pickup. It's a bit like a microphone. It picks up the vibration of the string right here. So I would find the same node somewhere here, but it's pretty convenient to find at the 7th fret. Let's check that. And yes, we can see at the position of the 7th fret, we indeed have a node on this symmetrical thing. And this relates to 3/2 times 1.5 times the frequency of the 2nd mode, and this is the 3rd mode. Okay. So next thing that I did, of course, was to dampen the string at the position of the 5th fret, right? And this would relate to this line right here. And then we'll see, as expected, this cuts the overall length into 4 bits. So it quadruples, I guess you say. It doubles the double of the frequency. This would again be the same musical note, but 2 octaves up, also called E. And again, then you can continue and continue. But again, what actually happens is when you play a musical note or when you just pluck the string, is that all of these modes happen at the same time. And this is what makes the guitar string sound like a guitar string, not just like a computer sine wave generator. And of course, on a real instrument, these different modes, or the intensity of these frequencies, are slightly different. This is why different guitars sound differently, depending on how they're constructed. And then if you're playing very old strings, for example, if they're dirty, there's more damping, which has a greater effect on the higher frequencies. So this is why old strings, for example, sound somewhat dull. Okay, so that's enough of guitars here, but again, I think it's pretty neat example to explain and make it more understandable what we're doing when we're doing a modal analysis. Basically, we want to identify all these different modes with a guitar string. We can identify them by dampening the lower modes, so we can hear the higher modes. Of course, in a technical context, that's not so easy. And with any other technical part that that can vibrate, the different modes might not be harmonic to each other. So in the musical context, you want to hear a beautiful sound when all these modes happen at the same time. And we do find that it sounds harmonic and nice if all the modes have multiple frequencies of the original frequencies. Now, if we're looking at, let's say, a car body, if we're running a modal analysis on a car body, we want to know these modes because they have consequences. They might be bad for the strength or just for riding comfort if these modes are excited, right? So this is why we want to know about it, and we've discussed that at quite great length in the IDE lecture this semester. But of course, to find out these modes in an experimental way, you could try to excite them acoustically, or rather mechanically by exciting them with this frequency, or you run the analysis. So you can now already expect that at the end of your computer-based analysis, it should show you the different shapes and give you the different frequencies that come with the different modes. This is exactly what you can expect. And just to stay with the musical example here, I couldn't help it. This is also one analysis that I've asked Chinnawit to do for me a few months ago. This is what I call an unplanned or unwanted vibration in a musical context. Now, you might be able to tell this is a neck of a tenor saxophone with a mouthpiece at the end. And you should know that the thing that vibrates in a woodwind or in a wind instrument is not a solid body like a string, but it's the air column, right? So we don't actually want or plan, we don't plan the body of the saxophone to do vibrations, but it happens anyway. Just with a car, anything that happens in a cyclic way might excite mechanical vibrations, and also with saxophones, for example, the musical sound will excite the different modes of a saxophone. And this is just this is also from a modal analysis of this saxophone neck that I think is the first mode. And you can see, although the amount of deformation is of course extremely exaggerated, in reality it would just be a few tenths of a millimeter maybe at the end of the mouthpiece. But there are mechanical vibrations happening, and they have an influence on the overall sound of the instrument, of course, too. I call them unplanned vibrations because typically in saxophone design, this is not considered by the designer, and it might, if it causes major problem, the designer might understand, the producer might understand it has to do with solid body vibrations, and there might maybe solder a piece of metal into the curve of this neck right here, possibly in order to prevent this vibration from happening, to make this mode of this vibration disappear. So in the technical context, and of course we are studying mechanical engineering, there are billions and billions of examples. The internet is full of them. So I just quickly Googled something that would be a meaningful, nice example for a technical part, and I quickly found something. There's a web page that I've never seen before. Looks like some sort of sharing page. There's a lot of images here for technical or modal analysis on technical parts. This one is on a clutch disc, and this is a cool example because at least one student, but I expect two students that are joining us today, will be working on this for their internship and master thesis. Okay. By the way, Kuhn Austin, I'm still waiting for the reply. I'm going to send them a reminder today. Okay. So here you would see what I believe are the first 4 modes of this clutch disc, which is made from. Actually, I'm not sure. It might be steel. It might be this typical composite plastic. But I think this might be the steel part because it has this this elastic bit in the middle. So the first mode would just be bending. You can see the red bits would be moving the most, and the blue, you can see on the scale, blue means 0. So that would represent a node. The blue end would be the node, and it kind of folds itself like a butterfly for the first mode. The second mode, now I see the headlines, total deformation. There is no number 2, but I would still guess the image on the top right is probably the second mode. And this is the center of this disk is not moving, but that's probably because they constrained it. Not so sure about that. And then the whole thing vibrates around that. So that would be a typical motion of a loudspeaker, around loudspeaker with a membrane vibrating. But in loudspeaker, it's the other way around. It's the outside ring that's constrained and the center moving in and outwards. Then the total deformation 4, that's bottom left, would be the next mode, which is interesting. It seems like a torsional deformation. You can see 2 blue lines crossing each other. So so that would be the node lines where there's no movement. And then you can see the opposite, well, it's not edges, I don't know how to call that. The opposite outside of this round disk are moving in that way. So it appears to be a torsional mode in a way, or you could say it's like two bending modes overlain 90 degrees. And then the last one, total deformation 6. I'm not sure if there are modes in between of that, and they're just not shown because they're not so interesting here. That would be stepping the previous one mode up 1 bit. So here you have 3 lines, 3 nodal lines, and it's I don't even have a word for this shape that is resulting. Typically, the software can give you these modes as videos, as animations, so it's easier to understand what's going on. But I think even from these images, you can tell pretty well what's going on. So I believe even the ones who haven't joined Ajahn Kemapat's vibration class this semester, you should now understand well enough what we're talking about. To perform such analysis on FEM software is actually pretty easy. It doesn't require many more steps than just linear elastic analysis, but of course you have to choose a few more properties for the analysis, and this is exactly what Chinnawit will demonstrate to you in the next bit. And he will first run a very general analysis on this piece of metal that he calls the cantilever beam. The material properties are pretty close to steel. So I think he calls it stainless steel. You can see the elastic modulus is slightly lower, but it doesn't matter really. So it's these density and elastic modulus is somewhat less than regular steel. And as boundary conditions, he's going to fix one end of the beam. So that's extremely important. This piece of metal will behave completely different if it's unconstrained or constrained on both ends, or only one end. So here it's going to be constrained on just one end. So you can already imagine the first mode will be like this winking motion from one end, and there's going to be more modes, of course. And he's probably going to look at the first 6 modes as this slide says. And then the second example that is also going to be the assignment will be, again, a musical application, of course, a tuning fork. Now, this is a piece of metal that is designed specifically to give you one musical pitch to tune an instrument. Now, this has been in use for hundreds and hundreds of years because we didn't always have electronic tuners, and we didn't always have mobile phones with apps that can work as tuners. Now, we of course all have that, but this tuning fork is the standard musical way to do it. So our modal analysis should give us a specific frequency for this model, and I've given you on the shared drive, I've already given you the Creo model for the assignment, and I've also given you, I think it's a step version of that same geometry. So you will be able to use that for the first run of the analysis. And again, the lowest mode that you can find its frequency will be the frequency you can hear as a musical pitch. So that relates to the node that is typically stamped, the note, not the node, the note, the name of which is stamped onto that thing. So typically that you'd expect that to be 440 frequency. So that relates to an A, I think this one. So that's my guitar again, but because I think the low A, that's 220. Oh, sorry, so it's probably this is 440. I always get mixed up with the different octaves. I think this would be the sound of A 440 tuning fork, or pitchfork as it's also called. I think the model you have, this is one that I borrowed from Ajahn Kem, and I hope, I'm not sure I've given it back already. When we did the analysis, we found out that this is a really weird tuning fork with a weird musical pitch somewhere between C sharp and D. So we were joking about the application of that tuning fork. Now, your assignment, your homework will be to change the original design of that given pitchfork to achieve a specific frequency. And again, so I'm forcing you to learn about music a bit. So Ajahn, yeah, let's call him Ajahn Chinnawit today, because today he's your teacher. He chose different musical notes for all of you. This is your assignment. And you are allowed some tolerance. Basically, it's a matter of iteration, right? So you'll start with one design. You'll run the modal analysis. As a result, you'll have the frequency of that design, and then you'll go back to change the design, which of course is just adding material or taking material away. So you could make these two prongs of the fork longer, or you could make them thicker. So there's more degrees of freedom. And then you'll, in an iterative kind of way, you'll approach the frequency that you have to achieve. And this is us being mean again. We don't give you the frequency, we give you the musical note. So you have to look up what that frequency is, but that's pretty easy. The internet is full of such tables.
So let's start in the ANSYS workbench. Okay, do you see my screen share, right? Okay, I will delete all simulation that I just try to simulate the modal analysis. Okay. So first step, you have to select the modal analysis module, click and drag into the project schematic, right? For the first, I refer to the Dr. Alex slide. Okay. We have a cantilever beam and the stainless steel or steel, whatever material that you want to add. But for this case, I assume that it's a stainless steel. So this is a material property of the beam, and this is a boundary condition. You have to fix one end of the beam and simulate the modal analysis of this beam. Okay, I just switch the share screen to. Okay, for the material property, you have to define in this entering data and right click and choose edit. Okay, this window show the material property that you will use to the ANSYS. For by default, the program select the structural steel in the library you can change the property by click. You can edit the density in this table. You can edit the Young modulus in this table. For this problem, I will change structural steel density to okay. And for the elastic modulus, you click the isotropic elasticity, and okay, it's default is a right value that we want to use in ANSYS. Okay. And Poisson ratio is 0.3 is the correct value. Okay. By finish editing the material property, you can close the engineering data window. So the geometry, you right click. So you have 3 options to define the geometry of the model. You can use new space claim to draw the 3D model in ANSYS, or you can use a new design modeler geometry to create the 3D model, or you can import geometry. So by this, for this case, I will choose the design modeler geometry in order to create the 3D model. Yeah. Okay. The first step, you have to create in 2D and then extrude the 2D sketch into the 3D, same as a 3D CAD modeler, any for any software that make from 2D and then extrude to 3D. I select for the XY plane, right click and look at the XY plane, and then click sketch, scratching, and choose the rectangle. Okay, so now next step, you have to define the dimension of this sketch, and you click dimension and click general. The dimension show the input. You have to input the height and the width of the sketch, the vertical and the horizontal line. From our problem, can I see the dimension? Okay. With 20 millimeter width and 10 millimeter thick. 10 millimeter thick. Okay. Before you input the value, you have to change the unit by click and change to millimeter. Okay. The beam long beam long the beam long have the 200 millimeter long. I will change this. Okay, after input the value in the to the sketch, and you click extrude, and then you can click the sketch. Maybe you may have to zoom in the sketch. Okay. Click this sketch and then input the long 200. Okay, after input 200 millimeter long, you right click extrude and then click generate. So the green tick appear. That means you already created the 3D model. So you can click the ISO view to see your 3D model. Okay. Okay, now you can close the design modeler window and then back to the ANSYS workbench again. Okay. The geometry is already created, and to next step, the model, you right click and edit. Okay. In the tree, the ANSYS show you have created the geometry, the material property already assigned to your model, and now you have to go to the mesh process. In mesh, you click the mesh and then element size. For this case, I will put around 5 millimeter. So if you can change the unit in the top of the menu bar by click unit and and change to millimeter if anyone selects the mid by default. You can change to millimeter. Okay. After input the 5 millimeter of element size, so you can right click mesh and then update or generate mesh. Okay, for this case you can click generate mesh. Okay, our model already mesh expand the modal module. Okay, for this case we fix one end of the beam. I will show you how to define the boundary condition. Just right click the modal, insert, and then fix support. I will fix this size, click this surface, and then click apply. That means this size already define the fixed support type of the boundary condition. Okay, so next step, click the ANSYS analysis setting. The option, by default, the option input the 6 mode to find. That means the program will find the 6 mode of the vibration of the cantilever beam. So you can change if you want to see more vibration mode of the beam by click increase or decrease. Another option, you can click the limit, search for range. That means you can define the minimum or and maximum frequency of the vibration of the beam. You can change, but for this case, I select no, because I would like to see the 6 mode of the beam. Okay, after finish this, you can click the solution, right click, and then solve. So the solution show us we have 6 modes of the beam. If you want to see the animation, the shape, you can right click this graph and then select all. So, and then right click again and create mode shape results. The 6 mode shape will appear in the solution. So you can right click in the solution again and then evaluate our results. The green tick will appear. That means you can see the animation of the beam that's vibrate in each mode. For the first mode, right, and you can see this is the first mode of the vibration. The second mode, let's show you, this is the type of the second mode. And for the third mode, the fourth, the fifth, you will see the twist. And the sixth mode. You also see the frequency in each mode. Okay, this is a first problem that I show you for the first problem. Okay, just finished. There any person cannot catch up with me? Please, please tell me if you cannot catch up with me. Okay, I will shift for the second problem for the tuning fork. I will close the window. Okay, for the second problem, we will simulate the modal analysis of the pitchfork or tuning fork, whatever you say. Okay, I just click modal again and then click hold and drag. Okay, I will change the name for tuning fork. Okay. For this case, I will define the material property in the pitchfork as a stainless steel. Right click and edit. You can click the engineering data source, and then in ANSYS we have many types of material in the library. You can click the general material, and the second table you see the stainless steel in this, and then click add this material to our library. Okay, the icon book appear. That means we already add this material in the ANSYS in our library. Okay, just close and import the pitchfork. I think you already download the CAD file in your PC. Right click in the geometry and import geometry. Browse. Okay. The green tick appear that we already import the CAD file into the geometry. Okay. You right click the model to open the modeler again.
What was the name of the material?
Name of the material? You mean the stainless? Or
yes, stainless steel or structural
steel. You can assign the material later in the modeler.
Okay.
Okay. I will switch the share to the Okay, the pitchfork already import in the modeler. Okay, so the material, you expand the material option and you see the stainless steel or structural steel, right? So for you, if you want to assign the structural or stainless steel, you
I can see your screen.
oh, sorry. I will show the screen. Did you see my screen now?
Yes.
Okay, right. You can click geometry and then expand the properties. I will show you. Okay, click tuning fork and then you see the material assignment, right? And you can select the stainless steel. That means now stainless steel already assigned to the pitchfork. Okay. Now we skip to the mesh process. In mesh process, you can edit the size of the element. For this case, I assume around 2 millimeter. And right click mesh and click generate mesh. Okay. So now we already mesh. Click modal. So for the pitchfork, you don't need to define the boundary condition at any surface of the pitchfork. For the analysis setting, you can change the maximum modify to 12 because the first 6 modes, that means the rigid body rotation or rigid body translation, because we have 6 degrees of freedom. Okay, we change to 12 and then click solution, right click and solve. Okay, so that means the first 6 is the value is nearly 0 frequency, nearly 0 hertz. That means the pitchfork translation or rotation itself. Okay, and the first mode of frequency of the pitchfork begin of the 7th mode. That means the first mode of the pitchfork is around 290 hertz. So right click, select R, and then create mode shape results. Same as the last problem, right click and evaluate our results. Okay, I will show you for the first mode. You see, right? This is a translation and rotation combined together of a pitchfork. Okay, I just begin for the first mode. When you hit the pitchfork, the pitchfork will vibrate in this shape. Okay. You can reference for the first mode as a the frequency, the your frequency that you already assign to decide the pitchfork. You can change the dimension of the pitchfork and then simulate and find the 7 mode and see the right frequency that you already assign to the assignment. Okay, I think is enough for the demonstration of the modal analysis by using the ANSYS software. And are there any questions?
I don't have any questions too. Only one comment maybe.
Yeah.
So the reason why we don't constrain the pitchfork is because it's not constrained in real use, right? I cannot find my own pitchfork, but when we strike the pitchfork, we hold it between 2 fingers, we strike it somewhere.
Yeah.
And even if we hold it between 2 fingers, that's almost no constraint. So it's basically moving unconstrained. So we did last year, Chinnawit and I, we did constrain it. It just gives you different modes and different frequencies. So that would just be wrong, right? Okay. So that was very concise. Thank you very much, Mr. Chinnawit. That will enable me to also use FEM software in the future.
Okay.
Thanks a lot.
Okay.